Under the Canadian Space Agency Space Technology Development Program, DPL Science has developed a unique scientific instrument, the Dielectric Deep Charge Monitor. In this 6-minute overview, we will briefly describe the instrument, its principle of operation, typical test results, and the application of the instrument as a spacecraft early warning electrical discharge device. The Dielectric Deep Charge Monitor is an instrument that significantly improves spacecraft health and safety by providing users with advance warning of a possible electrical discharge due to deep charging. The instrument provides real-time telemetry, giving important information that enables users to take measures to mitigate the effects of spacecraft deep charging. The Dielectric Deep Charge Monitor consists of an electronic housing and a sample holder. The electronic housing contains the instrument electronics. The sample holder contains the dielectric test sample, which replicates a possible breakdown site on the spacecraft, as defined by the user. The Dielectric Deep Charge Monitor is small, lightweight, consumes low power, and is available in a radiation-hardened design suitable for geostationary orbit. The Dielectric Deep Charge Monitor is mounted on the outer surface of the spacecraft, with the sample holder exposed to the space environment. This instrument is also used to perform ground-based characterization of materials for spacecraft charging assessment. The use of the Dielectric Deep Charge Monitor is a 3-step process. Firstly, the user identifies the dielectric material of interest, for example, a printed circuit board substrate, a cable harness insulator, or any other dielectric used in the construction of the spacecraft. A dielectric test sample is prepared and integrated into the instrument. Secondly, a ground-based test under simulated space environment conditions is performed to obtain information on the breakdown field stress of the dielectric test sample. Thirdly, the instrument is mounted onto the spacecraft with the dielectric test sample exposed to the space environment. Once in orbit, the instrument telemetry provides the DC potential of the dielectric test sample in real time, which is easily compared to the measured breakdown voltage of the dielectric. The approach to a known breakdown voltage alerts the user to a possible future electrical discharge, giving the user an opportunity to take safety measures to protect the satellite. The continuous monitoring of deep charging effects on dielectric materials assists users and satellite operators in controlling the hazardous effects of spacecraft deep charging, ensuring the safe and continued operation of their satellites and payloads. In order to perform the ground-based testing, a special test facility was developed by DPL Science. The test facility provides a means to characterize the dielectric test sample under simulated in-orbit energetic electron environment conditions. An adjustable strontium-90 beta source is used to simulate the energetic electrons of the space environment. A vacuum pump provides the vacuum condition of space, and a thermal plate allows for testing over temperature. This slide shows a typical test plot. In this test, a 60 thou polyamide test sample was used. Under vacuum condition and with the dielectric test sample installed, the unit was irradiated with the strontium-90 source. As soon as irradiation begins, we observe that the dielectric test sample begins to accumulate charge. After continuous irradiation over a 3-hour period, the irradiation was blocked by closing the strontium-90 shutter. As soon as irradiation stops, we observe a charge decay in the dielectric test sample. At the hot temperature of plus 75 degrees C, we also observe that the decay would have continued had we extended the recording time. This plot shows the results of a similar test, but performed at the code temperature of -40 degrees C. Again, we have the same 60 thou polyamide test sample installed in the unit. The unit is brought to vacuum, then irradiated with high-energy electrons. The charge accumulation on the dielectric test sample is rapid, taking only 30 minutes to reach -18 kilovolts, compared to 3 hours when the test was performed at the hot temperature of +75 degrees C. When the shutter to the strontium-90 was closed, we observed no charge decay in the dielectric test sample, unlike the continuous decay that was observed in the previous slide when the test was performed at hot. The two plots demonstrate the significance of code temperature on the charging of dielectrics and the benefit of in-orbit real-time monitoring provided by the instrument. Based on these two test plots, we can see that the cryogenic effect on dielectric deep charging would be dramatic. An important aspect of the instrument, and a major design challenge of the instrument itself, is that the dielectrics used in the construction of the instrument must not induce error in the measurement. The instrument must be capable of detecting accurately the charge accumulated on the dielectric test sample. This plot shows the results of a test that was performed on the instrument with no test sample installed. Under vacuum condition and at a temperature of -40 degrees C, the instrument was continuously irradiated with high-energy electrons over a 5-hour period. As we can see from the plot, the output voltage of the unit did not change over time. The output remained constant at 14 volts, which is the nominal offset of the unit. This test demonstrates that the charge accumulated on the dielectrics used in the construction of the instrument does not introduce error in the measurement. Therefore, the instrument accurately measures the charge accumulated on the dielectric test sample. In summary, the dielectric deep charge monitor is an instrument that significantly improves spacecraft health and safety by providing users with advance warning of a possible electrical discharge due to deep charging. The instrument provides real-time telemetry, giving important information that enables users to take measures to mitigate the effects of spacecraft deep charging. Recently, 2 space-qualified units of the dielectric deep charge monitor were delivered to the Canadian Space Agency, a flight unit and a qualification unit. The design and performance of these 2 units exceed expectations. Both units passed environmental and life testing without failures. The instruments were characterized in a test facility designed by DPL Science. Few spacecraft charging test facilities exist worldwide. The DPL Science facility is the only one in Canada with radiation and thermal vacuum capability. The continuous monitoring of deep charging effects on dielectric materials assists users and satellite operators in controlling the hazardous effects of spacecraft deep charging. If you would like more information about this instrument, we invite you to contact Mark de Peyerbrin at DPL Science.